t-test problems for the mean will involve also the traditional method and the p-value method. I will put those lecture notes on the document camera. As a reminder, you will go to stat and test and t-test. Basically ask you for the same information if it's raw data or statistics. The claim, the sample mean, the sample standard deviation, the sample size, the alternative hypothesis not equal to, less than, greater than, and then calculate. So stat and test number 2 for these t-test problems. T-test problems are when sigma is unknown and at the very same time n is less than 30. Both conditions have to be satisfied. I'm going to focus on traditional method first and using the t-table to help you find those critical values, which is step number 2. The manager of a car rental agency claims that the average mileage of cars rented is less than 8,000. Less than. A sample of 5 automobiles, that's your N, has an average of 7723, that's your X bar, with a standard deviation of 500 miles. At alpha equals 1%, is there enough evidence to reject the claim that the average mileage of cars rented is less than 8,000? Notice how it says a sample of 5 has an average of 7723 with a standard deviation of 500. In one whole sentence in which they're talking about the sample of 5, they give its average and its standard deviation. It does not say sample standard deviation, but it is sample standard deviation. S is 500 miles. N is 5, X bar is 7,723, and S is 500. Test this claim at 1%. Alpha is 0.01, level of significance. This is a t-test because both sigma is unknown. They do not give population standard deviation. They give sample standard deviation. And at the very same time, n is less than 30. Both conditions are satisfied. When you go to your claim and you notice that it claims that it's less than, and you go to your phrases, less than has this symbol. So you look for this symbol with your setups, and it's a left-tailed t-test. The null is greater than or equal to, but the alternative is less than. And I write that here, and the claim is the alternative. Connect math will have mu equal to 8,000 in the null, but less than 8,000 in the alternative. The claim is still the alternative hypothesis. This is Connect Math, or the new edition of the textbook. The null is always equality. The next step is the critical value found from the t-table, and that's going to determine our rejection region. This is a left-tailed test, so our critical value should be negative, and we will be utilizing the properties of the student t-distribution. Here are the steps. Degrees of freedom tells you which row to go to. Sample size -1, so isolate row 4. So let me show you the table, and I'm going to isolate row 4. If you notice, this is a one-tailed test. It's a left-tailed t-test. So we look up our alpha here, and our alpha was given to be 1%. So one-tailed alpha, that means it's a left-tailed t-test, or a right-tailed t-test, but this one was a left. And here's your alpha, which is given 0.01. Degrees of freedom 4. Your two fingers meet at 3.747. You have to make that a negative 3.747 because this is a left-tailed t-test. And that critical value is going to be negative 3.747. Degrees of freedom. Left-tailed, one-tailed alpha is 1%, but it's left-tailed, so it's a negative 3.747. And then that brings you to your picture here. You have a t-axis, a mean of 0, and here's your critical value. And there's your rejection region shaded, determined by your critical value. It says make negative since it's a left-tailed t-test. The t-table, inside the table, all of those values are positive, but they can be negative test statistics as well, or excuse me, negative critical values as well. If it's a two-tailed t-test, you'll have two critical values. One is negative, one's positive. If it's right-tailed t-test, you'll have one critical value is positive. If it's a left-tailed t-test, you'll have one critical value, and you'll make that number negative in the table. The next step is the test statistic, and that's t this time, and you round up 3 places because it is a t. And 7723 minus my claim of 8,000 divided by 500 over the square root of 5. Sample variance was 500, sample size 5, claim 8,000. It was less than 8,000 was the claim, and then my sample mean. And to 3 places accurately, you get negative 1.239, and I'll put that in the calculator. And you put that test statistic in your picture. But that's 7723 minus 8,000 equal divided by 500 over the square root of 5. Equal. You do need parentheses around 500 divided by the square root of 5. Negative 1.239 to 3 places accurately. Placing it in the picture, negative 1.239 is larger than a negative 3.747. So it falls in the non-shaded, non-rejection, non-critical region. Do not reject the null hypothesis. And the null statement again said greater than or equal to 8,000, so we're not rejecting that null statement. That means there's not enough evidence to support the claim that it's below 8,000. You can still go to that sheet. Eventually you'll catch on to these summaries, but if not, always go to the sheet. The claim was the alternative that it was below 8,000, and we do not reject the null. There's not enough evidence to support the claim that it's less than 8,000. So here. There's not enough evidence to support the claim. And so the possibility of mistake here is beta, type 2 error. Next problem. Well, let's put this one in the calculator. Stat and test. And it's a t-test. The claim is 8,000 from step number 1. The sample mean is 7723. Sample standard deviation 500 miles. Sample size 5. It was left-tailed, so less than claim, less than mu sub 0 in the middle. And then calculate. Test statistic is negative 1.239 to 3 places accurately, so look for that t, that's your test statistic. P-value 0.1416 to 4 places accurately. We may get something different from by hand using the table. But with traditional method, the only thing that it's going to give you for traditional is the test statistic. Problem number 2. Cushman and Wakefield reported that the average annual rent for office space in Tampa was $17.63 per square foot. A random sample of 15 rental properties with a mean rent of $18.72 per square foot and standard deviation of 364 was taken. At alpha equals 5%, can it be concluded that there is no difference in the rents? Okay. This one is saying there is no difference. We are testing the claim at alpha equals 5% that there is no difference in the rents. You can go to your phrase sheet to look up no difference. And that means equality. Is equal to, is exactly the same as, has not changed from, is the same as. But when I say no difference, I think the sheet that says it best would probably be here. Equal to means there is no difference. Not equal to means there is a difference, there is a change. So this is a two-tailed t-test. Equal to versus not equal to. Cushman and Wakefield claimed that the average annual rent for office space in Tampa was $1,763. The word was means equal to, and they did report something. A sample of 15 rental properties had a mean of 1872 and had a standard deviation of 364. Again, that standard deviation does not say sample, but it refers back to the sample of 15. It's one whole sentence talking about the sample of 15 with a mean and with a standard deviation. So that's S naught sigma. Alpha's 5%. But sigma is unknown and N is less than 30, so it's a t-test. The claim is the null, there is no difference. There is no change, that means equality. With a two-tailed t-test, you will still go to row degrees of freedom, 15 minus 1, which is row 14, and block it off. And look up your alpha of 5%. Remember, alpha determines critical values. So row 14. This time when you go to look up your alpha, go to the two-tailed alpha row, and there's your 5% there. Row 14. Your two fingers will meet at 2.145, and you'll make that a plus and minus because it's a two-tailed t-test. 2.145. So two-tailed alpha, two-tailed test, alpha was 0.05. Degrees of freedom 14 because my sample size was 15, plus and minus 2.145. And those will mark my two rejection regions here, two critical values. Test statistic. The test statistic is my 1872 minus my claim of 1763 divided by my sample standard deviation S divided by the square root of N. And that's 1.160 to 3 places accurately, which is smaller than the 2.145. So do not reject the null statement that says that it's equal to $17.63. By the way, this null statement was the claim, and we're not rejecting the null statement. Therefore, the summary statement, the claim was the null, do not reject the null. There's not enough evidence to reject the claim. Doesn't mean the claim is correct. There's just not enough evidence to reject the claim that it is or was 1763. Actually, there's not enough evidence to reject the claim that there is no difference in the rents. No difference means equal to 1763. Okay? The next problem, and you can plug that one into your calculator, and you would get the test statistic that we received here. But the next problem is the p-value method for the t-test, and I'll show you how you do that. Again, remember the steps will be that you state the null and alternative hypotheses, determine test statistic, determine p-value from test statistic. We'll use the t-table this time. Make the decision based upon the comparison of alpha and p-value to reject or do not reject the null, and the summary statement. Step number 1. An officer states that the average fine levied by a safety office against companies is at most $350. At most. A company owner suspects that it's higher. This is a problem that I would say has a twist to it. It's not, the claim is not what you necessarily think it is. An officer states that it's at most $350. At most means less than or equal to, if you go to your phrase sheet, less than or equal to. A company owner suspects that it's higher, which means greater than. She samples. Who samples? The company owner, who's suspecting that it's higher. 12 companies in, and finds that the average X bar is 358. The sample standard deviation S is $16. Here we go. Test the claim that the average mu is higher than, greater than 350 at alpha equals 5%. So the claim's not coming from the officer. The claim is coming from the company owner who's suspecting that it's higher. So we will actually go with the symbol greater than. And when you go to your setups, you have this type of test, a right-tailed t-test. The null statement less than or equal to is what the officer is saying at most, but the claim is all about what the owner is saying, higher than or greater than. So this is a right-tailed t-test, and the claim is the alternative. And so we set it up. This is a t-test because she samples 12 companies. The sample standard deviation is 16. Sigma is unknown and n is less than 30. For the test statistic, the 358 is the sample mean minus the claim above of 350. S is sample standard deviation divided by the square root of 12. You get 1.732. And remember, we didn't find critical values because this is the p-value method. So we jumped from step 1 to step 2, finding the test statistic. I will tell you that by hand, you cannot find an exact p-value when it's a t-test. You have to find something called a p-value interval. The calculator, TI-84, will give you an exact p-value, but by hand using the t-table, you only find something called the p-value interval. And it just gives you possibilities for what the p-value could be. Go to row 11 and isolate it. So sample size minus 1. And then you look across the row and find two values that encompass or sandwich your test statistic of 1.732. So let me show you the process. Here's our test statistic. It is right-tailed. So go to your t-table and block off row 11. Find the two values in that row that sandwich or encompass your test statistic. And again, your test statistic is 1.732. And you see that it falls here. 1.732, and that's positive, is your test statistic. Once you find the two numbers that bound your test statistic, sandwich your test statistic, encompass, whatever, the test statistic is between those two numbers in that row 11. Go to the top and remind yourself this was a right-tailed t-test. So bypass where it says two-tail alpha and go to the one-tail alpha because this was right-tail. And I tell my students to cross fingers. And really it's just something I say as something dramatic so that it causes students to remember that 0.05 is smaller than 0.1. So I say cross fingers because 0.05 is smaller. When you write your p-value interval, you will say that the possible p-values fall between 0.05 and 0.10. That's why I say cross fingers. And your p-value interval, if this were an axis, it would look like this, the graph. So the p-value can be any number in between here. But it cannot be 0.05, it cannot be 0.1, but it can be any number in between, which could be 0.06, 0.07, 0.09, 0.085, 64, but it cannot be exactly 0.05 and 0.1. So go to degrees of freedom. Sample size was 12, block off row 11. Find the two values in the row that sandwich your test statistic. Go to the appropriate either two-tail or one-tail, since it was a right-tailed t-test. Bypass two-tail and go to one-tail. Cross fingers. Your p-value is between those two numbers, 0.05, 5%, and 10%. That's your process for finding the p-value interval. And I kind of draw that out here. So smaller, larger. This says that we don't know the exact p-value by hand, but it does fall between those two numbers. The calculator gives you 0.0556, and your calculator p-value will always fall in this interval, which would help you rule out some multiple choice selections there, A, B, C, D, because I will be asking you for the p-value interval. You put in your claim for this problem, and it was 350. And then you put in your sample mean 358, your sample standard deviation $16, sample size 12. It's right tail, so let it blink on greater than and press enter, and then calculate. And your p-value by hand is 0.0556 to 4 places accurately. And that p-value does fall in this interval. Now, I want to tell you something. The p-value is not money. It's actually a proportion or percentage. But sometimes students do have problems comparing and contrasting. And so I say students would understand if this happened to be 5 cents and 10 cents, which is larger. And I think that students would understand that this is not money. But I think you would say this is about 6 pennies, right? 6 cents. And 6 pennies, if it were money, would fall between 5 cents and 10 cents. So you could think of it as money. Now, I'll tell you where this came about. I used to teach a young man that was hearing impaired. And so he had a sign language interpreter come to class. And it was the sign language interpreter that told me one day that the student actually was understanding this comparison only if they thought of it, he or she thought of it as money. Even though it's not money, p-value is not money. But if they thought of it as money, they could see that 0.05 comes before the 0.1 and that your p-value from the calculator is somewhere in between. So if it helps, think of it as money, but it's not money. So next step would be your comparison. Now, I personally love using the calculator p-value to make the comparison because it does make it a lot easier. But remember, alpha open box p-value, put your symbol here. You have two choices, either put greater than or equal to in this box or strictly less than. Your p-value is not 5%, it's not 10%, but it's somewhere in between. The calculator says it's almost 6%. So alpha is less than the p-value, or any possible p-value here, 6%, 7%, 8%, 9%, 10%. Alpha is less than. And if alpha is less than, according to the sheet, do not reject the null hypothesis if alpha is less than p-value. And the null hypothesis said less than or equal to. That means there's not enough evidence to support the claim that says it's greater than. That means that if you had to say which one would be more accurate, it'd be the officer over the owner. But you can't say for sure. The only thing you can say is that the claim is the alternative. The owner suspects it's higher. Do not reject the null statement. The officer says it's at most. There's not enough evidence to support the claim from the owner that says it's higher. And that's your summary. And this was from the owner. Beta is the possibility of making a mistake in this problem, not rejecting the null when it could be false. Next problem is also a p-value problem, but it is a t-test problem, and it's raw data. So I'll show you this. A new lab technician read a report that the average number of students using the computer lab per hour was 16. To test this hypothesis, he selected a day at random and kept track of the number of students who used the lab over an 8-hour period. The results were as follows. So I have 8 hours represented here, and students using the lab. 20 students, 24, 18. 8th hour, 23 students used the lab. So your sample size is 8. At alpha equals 5%, test the claim that the average is actually 16. Is actually 16 means equal to. So equal to versus not equal to would have to be your setup, and the claim is the null this time. It's a two-tailed t-test, and the reason it's a t-test, the sample size is 8. You would have to put this raw data in your calculator and find the sample mean of 19.6, and I rounded to the nearest tenth because my raw data values are whole numbers, and the standard deviation of the sample. They didn't give standard deviation anywhere. They didn't say sample standard deviation. They didn't say population standard deviation. So it's implied that you'd have to find S, sample standard deviation. Just like with the T intervals for the true mean, with raw data, you'd have to find S. I'm not going to put this in L1, but you could put it in your column. Those of you that don't have a TI-84, you're going to have to find S by hand using the formula way back in Chapter 3. But it is 3.0 to the nearest tenth because my raw data values are whole numbers. And that's the rounding rule from Chapter 3. Next step would be the test statistic, and that's the 19.6 that we calculated minus my claim of 16 divided by my sample standard deviation that we calculated divided by the square root of 8, and I got 3.394. P-value interval time from the t-table. You go to row 7 because your sample size is 8, and you isolate it. And you look across that row and you find the two values that sandwich the 3.394. So row 7, 3.394. Now this is a little bit tricky as well. The values in this row 7, the last value is 3.499. If you notice, these values are increasing, and the test statistic was 3.394. 3.394. So here we go. This one's not tricky. I thought it was the case where the test statistic falls off the table, and we will discuss that. Sometimes the test statistic actually falls off the table here, and that's a special case. But the test statistic is 3.394. So it falls between these two values. You go to the top and you stop here at two-tailed alpha because this was a two-tailed t-test, and cross fingers. The p-value is between 1% and 2%. So 0.01 less than p-value less than 0.02. Row 7, block off the two values that encompass your test statistic. Go to the one-tailed alpha row because it's a two-tailed t-test, cross fingers. 1% is smaller than 2%. And there's your p-value interval for that problem. The next step would be and here is a graph of the possibilities per p-value. By the way, the calculator gives you a p-value of 0.0115, and that is not money, but it's more than 1 penny, so it's definitely between 1 penny and 2 pennies, but it's not money, but thinking that it's money would help you. And then comparison time, alpha open box p-value, alpha was given to be 5% or 5 pennies if money helped you. And then your p-value is only somewhere between 1 penny and 2 pennies, but here it's 0.0115 from the calculator. So alpha is larger, but we would put greater than or equal to, so it matches up with the sheet. And greater than or equal to means to reject the null hypothesis. And the null statement said equal to 16. There is enough evidence to reject the claim that is equal to 16. Summary statement. Put your finger on the fact that the claim was the null and we decided to reject the null. There is enough evidence to reject the claim that the average is equal to 16. Here we are. Summary. The possibility of mistake here is alpha, rejecting the null when it could be true. Could be the possibility of a mistake, rejecting the null when it could be true. So there is enough evidence to reject the claim that mu is 16 hours. And that concludes the problems dealing with the t-test problems for the mean, the traditional method, and the p-value method. I wanted to show you an example of when it runs off the table, when you're finding the p-value method and your test statistic actually runs off the table. I think that example is covered in class lecture. I don't have it here in the actual lecture notes. So do come to class and make sure you understand what happens if the test statistic you're looking for actually is falling off the table, which means it's larger than the last value here in the row. It's not that difficult, but it is a special situation, so we have to cover that. The next lecture will be all about proportion testing. That lecture will not be difficult at all. Proportion testing goes back to using the z-table because it's a type of z-test. And I'll go ahead and tell you that with the calculator, you'll go to number 5, one prop z-test. And you'll put in your claim of p sub 0. That's coming from step 1. The parameter changes to p, not mu. So on your sheet here, you will have p equals a number, p does not equal a number, p less than or equal to a number, p greater than a number, p greater than or equal to a number, p less than a number. Proportion. Still two-tailed, right-tailed, left-tailed, but it's p instead of mu. And there's your claim. You give your x and your n because you're telling the calculator how to calculate p hat, sample proportion. And then the alternative, not equal to, less than, greater than, and then calculate. It'll give you the test statistic and the p-value, and those are found from the z-table. So proportion testing is not difficult at all because we do go back to the famous z-test or the z-table, which you should know how to use by now. That means we'll be going back to invert the norm or normal CDF. We will be able to find a specific p-value from the table when it comes to proportion testing. Because it is the z-table, you can find a specific p-value from the z-table. So proportion z-testing, you can give a specific p-value once again. And there's not a lot of new information when it comes to proportion testing, but that will be the next lecture. So stay tuned. God bless you. Study up. Come to class. Take notes. And let me know if I can help you with any of the information. Have a great day.